and I'm very glad to introduce Alessandra Frabetti, Universite Claude Bernard de Lyon, that will speak about non-commutative renormalization Hopf algebras. Thank you, Alessandra.
Thank you very much, Paolo, for inviting me. It's a nice occasion for me to present this work to people precisely working on non-commutative geometry and related to physics. My work is related to both these subjects, but not really in the usual sense. And so I'm very glad to present it because I'm pretty sure that it could be related to some other approaches. But still, I had no time exactly to look at all this interplays. And so, well, it's a good occasion for me to present it. So I would like to talk about renormalization Hopf algebras, which are Hopf algebras appearing in renormalization in quantum field theory. And so the usual Hopf algebras are commutative. These are the Hopf algebras introduced originally by Connes-Kreimer, and then later on introduced in many other theories besides that of the toy model by Connes-Kreimer, which was the scalar phi-3 theory. But all of them are commutative. And so what I'm introducing is a non-commutative version, which requires a new principle in algebraic geometry somehow. So there is a geometrical counterpart to this introduction to this non-commutative set, which can be interesting for the community. So my motivation is the following. In the theory of renormalization of quantum field theory, there are two big approaches from the point of view historically, I would say. Of course, the problem of exploding integrals, some of the diverging integrals appeared in the 40s, and it was together with the foundation of quantum field theory, in fact, and Feynman introduced his graphs in part to solve the problem of finding the corrections to these terms which were not appropriated. And so the first formalization of this in a global settings was done by Feynman Dyson in 49. He showed for quantum electrodynamics that a theory with a given Lagrangian is renormalizable if all the counterterms computed for the graphs can be summed up in few factors which are related to each term of the Lagrangian. And these terms are called renormalization factors. So they are formal series in the powers of the coupling constant. And the coefficients of the series are computed using the counterterms of the graphs. So on the other side, there were attempts for computations of these graphs, which were giving the corrections to the Green's functions, to the correlation functions. And then there needed more than 10 years to prove a formula, which is now called the Forest formula or the BPHZ formula from Bogolyubov, Parashuk, Hopf, and Zimmerman, who proved it step by step, which is a recursive formula to compute these counterterms for graphs, which have not only overall divergences, but also subgraphs. Subgraphs containing subdivergences, I would say. So there are these two approaches, a kind of global one, considering the whole of renormalization factors seen as formal series in the powers of the coupling constant. And then there is a practical approach to the computation of counterterms for each graph, which is this Forest formula. I would like to show that the relationship between the two is a relationship which is very well known in mathematics, which is a duality between groups and their coordinate ring. So in order to do this, when I realized it, working on the subject of Hopf algebras for renormalization, which was introduced by Connes-Kreimer in 2000. So they introduced a Hopf algebra on Feynman graphs. which was exactly a mirror of this BPHZ formula. So I will show it later on, and you can see that it's just the same formula directly computed on the amplitudes or as an algorithm on graphs. Okay, so this Hopf algebra was commutative in the origin, and when one has a commutative Hopf algebra, there is some group underlying the commutative Hopf algebra. So there starts my work around 2000s. I tried to adopt the group point of view on the background of this Hopf algebra. And the group point of view is that there exists an algebraic group, which is in fact infinite dimensional. So it's a proalgebraic group of combinatorial series. So it's a kind of bad, I mean, it's a bad group in the sense that it's an infinite dimensional group, but it's kind of stupid because the underlying vector space is a linear space. So the underlying space, sorry, for the group is a vector space. So it's a flat group, but still it's infinite dimensional. It is a proalgebraic group. And it's not very interesting for usual geometry, but it becomes interesting for such infinite dimensional geometry. So the mathematical point of view underlying this physical situation is the existence of some groups and their Hopf algebra of the coordinate ring somehow of these groups. In order to understand the exact situation and the implication for physics, I will split this diagram into some levels of reality and virtuality in the following sense. One can split already these four cases on two plans. One is the plan of the real world, where the real series exist. These are series which have a meaning in physics. They are really Green's function. And so beside the fact that they must be renormalized, so they contain some parameter, which is a regularization parameter, which makes them existing at any scale, even in the scale where they usually diverge. So they really describe events, physical events. So one can measure the precision by changing the scale and then measuring how much this scale, which defines the running coupling, how much the scale is relating to the running couplings of the theory. So somehow the energy scales changes the series, but all the series are real. They really do describe something. On the other side, there is a kind of virtual word, which is the word introduced by Feynman when he introduced the Feynman graphs by saying that from a point X in space-time to a point Y in space-time, there is an event happening. In this event, we don't really know what happens. With a certain probability, a particle will be emitted, and this is, of course, a virtual particle. And then some other particles will be emitted, and the whole event, a whole bunch of events, which are all virtual, are going to happen with certain probability, and we really know nothing about them. We just see the input and the output, and have a blue box, unknown box inside. So the virtual world here corresponds to a list of devices made for computations. And this includes Feynman graphs, but it also includes all the tools coming from mathematics, like the Hopf algebras and their dual groups in the sense, in the literal sense of algebraic geometry. When one has a commutative Hopf algebra, then each element in the Hopf algebra is a coordinate. It's a local coordinate for any element of the group. And then one has to invent the group which is dual to this Hopf algebra. So all this falls into the world, into the virtual world. And so what I'm interested, of course, is what is the mirror of this virtual world in the real world. And so what I'm going to talk about is the relationship between these tools and similar tools which could be defined for real series, in the sense of series which are really describing existing events. And so what happens is that on the level of Hopf algebra, the Connes-Kreimer Hopf algebra, which is defined, which is generated by Feynman graphs, contains a Hopf algebra, which is called the Faà di Bruno Hopf algebra, which is just spanned by integer numbers. It is the Hopf algebra of the coordinate ring of formal diffeomorphisms. So formal diffeomorphisms do form an algebraic group, a proalgebraic group, whose elements describe real events. And so the mathematical relationship is that the Faà di Bruno Hopf algebra is a sub-Hopf algebra of the Connes-Kreimer one. And on the dual side of groups, the groups of combinatorial series can be projected onto the group of formal diffeomorphisms. So this group of formal diffeomorphisms are exactly the groups describing the renormalization of the coupling constant in the sense of Dyson. Okay, so then my boxes here are filling up the two parallel words, the real and the virtual words. One can ask what is the best device to make computations in the real world. Well, it would be a kind for computing the counterterms of the graphs, so the renormalization factors. Of course, it would be to compute something directly on the real world plan, which amounts to define a formula, which is a similar formula to the BPHZ formula, but which is recursive, not on each graph, not on each Feynman graph, but on the sum of Feynman graphs with a given number of vertices, which corresponds to an integral series. And so one of the effects of the introduction of this Hopf algebra for renormalization, from my point of view, is the possibility to make computations directly on integral series, and therefore to simplify these forest formulas. Okay, so this is one effect. Of course, one can ask, what is the last box here? Is there any last box here in the virtual plan? Yes, of course, one can define the group, which is formally dual to this BPHZ Hopf algebra, and formulas related to that. And in fact, one can do it, but it's not really very useful from my point of view in physics, so I haven't done it. But on the other side, on the mathematical level, the group here, the group of combinatorial series, which is on the plan of devices, this exists. It has been introduced by Connes-Kreimer during their computation. So the physical interpretation of this group here, on this sense, it could be done. But from my point of view, it's not very interesting. Okay, so my plan for this talk, this is the motivation. My plan for this talk is to make a little bit of introduction to all the ingredients I need. So first of all, to talk about this renormalization need in quantum field theory, starting from Dyson renormalization factors, and then talking about the BPHZ formula and the Connes-Kreimer Hopf algebra. I will be very sketchy in order to give you an idea of what these ingredients are. And if you need more details, you please stop me and I will give to you the details. Then I'm going to the math level, and I would just recall what is a proalgebraic group. And then what is the proalgebraic group dual to this Connes-Kreimer Hopf algebra, which stands here. In parallel, I will have introduced already the Faà di Bruno Hopf algebra, and I will be finally able to talk about the duality between these two. So this duality concerns physics in two different settings. One is the setting of scalar field theories, for which all these group of series, so the coefficients of the series are scalar, And then there is a duality here, which is the last point I will talk about. There is a duality, which is just a classical algebraic geometry duality between an algebraic group and its coordinate ring. But this duality only holds if the series have scalar coefficients. And so what I'm going to point out is that for quantum electrodynamics and chromodynamics and gauge theories in general, this group require matrix values. So these groups are going to describe exactly the correlation functions, the green functions. So the green functions for fermions and gauge bosons have matrix values. So they lay in an algebra which is non-commutative. It's a matrix algebra. And so the basic duality, algebraic geometry duality between a group and its coordinate ring does not hold in this case. And one needs to make an extension. So this extension to algebraic geometry on non-commutative algebras exists. It has been done by algebraic topologists in the 50s. And I don't know why it didn't really have a lot of followers, but the main ingredients do really exist. They have been introduced by Daniel Kahn in the 50s, in 58. So he proved some important theorems on algebraic topology on the basis of these results. So I'm going to exploit these results to go from a scalar field theory to QED and QCD theories and present an alternative Hopf algebra and then an alternative duality for these theories. And then there will be a last problem. The last problem is that formally this duality theory between groups and their coordinate rings on non-commutative algebras doesn't really hold for groups. So the extension must relax the associative property of groups. So an extension of algebraic geometry in this sense is possible if we are ready to renounce to associativity in groups. And this is possible. So I'm going to show that the perfect object in which this extension can be done, which is called a loop by a very bad chance, I would say. It has been called a loop by Mufang in the 30s. So it has nothing to do with the physical loops, nor with the loop groups or the spaces of loops. Okay, nothing to do with that. It's an algebraic construction which replaces associative groups, so usual groups. So I will, at the very end, I will show you how we can get rid of associativity and set ourselves into the category of loops. And then we have a whole picture which really makes sense. Okay, please don't forget to stop me if something is not clear. So I'll start with an overview of renormalization in quantum field theory. So in quantum field theory, first of all, one needs to fix an algebra. And of course, this algebra is fixed starting from the Lagrangian, which contains all the information about the dynamics of the physical systems in terms of some physical parameters, which are the mass and the coupling. For instance, the charge, the flavor, and so on, and the field, of course. The field we are concerned with. For instance, I give here two examples, but I think that examples of Lagrangians for field theory are well known to everybody. So starting from this Lagrangian, we are going to fix the algebra, which contains the coefficients of the correlation functions. So the correlation function is computed as an expectation value from a ground state. So the vacuum, for instance. So if if the Lagrangian has an interaction part, like in this case, I have a coupling constant lambda here, then the correlation function can only be computed in a perturbative way. So there are, of course, a lot of attempts to define rigorously non-perturbative quantum field theory. And in specific cases, so for topological field theory in dimension 2 and many other specific cases, the attempts are succeeding. In general, there is no global procedure. So for the while, I'm sticking to a perturbative quantum field theory, a generic formulation where these correlation functions are formal power series in the powers of the coupling constant lambda. And of course, they contain also powers of the Planck constant because of quantization. But what I'm interested in too is the perturbative aspect of this series. That is, I'm taking care of the powers in the coupling constant. And if I fix a certain degree of the power in the coupling constant, then I will have here a partial sum of amplitudes in some Feynman graphs and with powers in the Planck constant, which are a finite number. So to be more specific, to make sense to this correlation function, as a formal asymptotic series in the power of the coupling constant, we have as coefficient here some amplitudes computed on Feynman graphs, which are the Feynman graphs allowed by the theory. So for instance, for the phi3 theory, we have some graphs corresponding to the kinetic term, which is the Klein-Gordon part of the Lagrangian here, plus some graphs describing the vertex term here, which is a phi cube. Okay, so they are 3 legs graphs. So we take all these graphs here, we put them together, and we construct all the Feynman graphs of the theory. And then we compute their amplitudes using Feynman rules. Okay, so the correlation functions are asymptotic series in the power of the coupling constant. The powers are they are computed counting the number of vertices of the graph. And as coefficients, we have the amplitude of the graph plus the powers of the Planck constant. Okay, examples of graphs then are computed starting from the free propagator, so the blank line. Here are 2 examples of free propagators which are computed for the phi3 theory and for the Fermion propagator in quantum electrodynamics. So what I want to point out is that the free propagator of these theories, that is the smallest ingredient in all these huge construction of Feynman graphs, is a scalar element. So it's a complex number if the theory is a scalar theory, but it is a matrix in the case of fermions, and then it will be a matrix for bosons as well. The matrix here is given by the Dirac matrix gamma mu, which is a 4x4 matrix. Okay, this is going to be important for the sequel. Okay, so these correlations functions mathematically are asymptotic series in the power of the coupling constant with coefficients in an algebra A, which contains the value of the amplitudes of the Feynman graph. So the whole series can then be written as a power series of lambda, the coupling constant, and the coefficients here, they are finite sums containing the amplitudes and the power of the Planck constant. Okay, the second ingredient I need for renormalization is the fact that some of these graphs diverge. So here is an example of the divergent graph in 4 dimensions. This is just phi3. This has the minimal possible divergency, which is called a logarithmic divergence, because if we integrate this term, we get a logarithm. So one can make a computation by using Feynman's rule for computing this amplitude. This graph, strictly speaking, is going to produce an infinity as a value. So in order to make sense of all these divergent graphs, the first thing to do is to regularize them, which means to introduce a parameter, for instance, a dimensional regularization parameter epsilon or a cutoff lambda. The cutoff just cuts the infinity here, which produces a divergence. The epsilon parameter here is more difficult. It perturbs the dimension. So this D4 here would be moved into a dimension 4 plus epsilon in order to make this amplitude finite, but containing this parameter. Then one makes the whole procedure of renormalization on the whole set of graphs, and then finally sends the parameters back to its value 0 or infinity, depending on which is chosen. So this is the need from quantum field theory. We need to renormalize graphs. So as I was saying at the beginning, in 49, there were global formulas describing this renormalization, which are Dyson's formula, which tells the following fact, that a theory is renormalizable if all the counterterms for all Feynman graphs appearing in this virtual creation of particles, if all these counterterms can be put together in a few series that is as organized, they can be organized in few series which are called ZIs, Z1, Z2, and so on, which correspond exactly to the terms in the Lagrangian. So these series have the following effect. If we rescale the physical parameters of the Lagrangian, so the field phi, the mass, and the coupling constant, into new physical, somehow unphysical parameters, which are called bare parameters, a bare field, a bare mass, and a bare coupling constant. If we call phi 0, m0, lambda 0 a suitable combination of these renormalization factors, and we read the Lagrangian, the formal classical Lagrangian, in terms of these bare parameters, then what we get is indeed the renormalized Lagrangian in the effective parameters. So this is the assertion by Freeman-Dyson. And moreover, Dyson gives exactly the formula which renormalize the Green's function. Not only the Lagrangian, but directly the Green function can be renormalized using these renormalization factors. And so the formula to renormalize the correlation function is the following. We start from the correlation function G, which makes no sense because it is composed of terms which diverge. Okay, it's an asymptotic series whose coefficients diverge. Okay, in order to make sense of it, we replace its physical parameters, mass, coupling constant, mass and coupling constant, by the bare ones, and we multiply by a certain suitable renormalization factor. By doing this in a suitable way, what we get is the renormalized correlation function directly. Okay, I then extract some mathematical interpretation of this. Here we are all dealing with asymptotic series. For quantum electrodynamics, it has also been proved that the series are asymptotic, in the sense that the series is not really analytic in the parameter in the electric charge being equal to 0. The electric charge equal to 0, it is on the boundary of the domain on which the correlation function is convergent. So it is not inside the domain of convergence. So a perturbation theory in terms of charge equals to 0 cannot really produce a convergent series. This is clear nowadays. So we are really dealing with perturbative asymptotic series. This is not the problem. Okay, so from this perspective, we are dealing with two kinds of series. On one side, we have renormalization factors, which by definition of them, so no, I'm not sure I gave the exact definition, but never mind. All renormalization factors start from the one, they start with one, and they add terms in the powers of lambda. And then there is this bare coupling constant lambda 0, which is a formal series of a different nature. It starts with the physical parameter, the coupling constant lambda, and then it adds powers of it. Okay, so they are two different series. One of the renormalization factors are invertible series with a pointwise product, while the bare coupling is a formal diffeomorphism with substitution or composition of series in the parameter lambda. And then this law here, which tells how this parameter, the renormalization, so the bare objects here, act on the correlation function in order to renormalize it. Well, the action is given by this somehow formal renormalization group. It's not the running coupling renormalization group, okay? So formally, this renormalization group in perturbative theory is just a semi-direct product of the coupling constant and all followed by all the renormalization factors zi's. We have to take them all at once and make them acting on the Lagrangian or on the correlation function. And the action is by semi-direct product group law. So the semi-direct product group law is the following. So let's take the case of only one renormalization factor just to show which is the law. So we need pairs, the coupling constant on one side and renormalization factors on the other side. So the law is the following. Suppose we start with a scale lambda. We move to a scale given by the coupling constant, which is the energy scale lambda 0. And then we do another renormalization to a second scale lambda 1. So how do the two renormalizations follow one after the other one? Well, they follow in this sense. The coupling constant here are just composed as formal series. The renormalization factors satisfy this semi-direct product law, which is to say that the one on the left, the z prime, is multiplied by the z, but only after the coupling constant lambda 0 previously acted on it. Okay, so we need first to compose lambda 0 with the coupling constant of the first renormalization, and then we can multiply the two. Of course, because we can only multiply series in the same parameter, which is the physical one, lambda, the effective coupling constant, lambda. Okay, so at the end, what we see is that this renormalization, to renormalize, we need two ingredients, the coupling constant renormalization and these renormalization factors. All of them are formal series with coefficients given by counterterms of divergent graphs. So we come here to how to construct this series. So these series are computed by computing graph by graph its counterterm. So we need the list of all graphs and we need to compute the counterterm for each single graph. This is the way to do it. And of course, physicists usually stop at the first order because it's too much, well, practitioner, I would say. Okay, there are some physicists who go to the third order, but they combination to the second or third order, they can take a lot of time.
Sixth or seventh.
Oh, okay, great. Congratulations. I asked in Lyon, and my colleagues in the Institute of Physics, they just stop to the first. They do not bother. Okay, anyway, so the computation of this counterterm for each graph can be done, for instance, with this BPHZ formula. And the formula is the following. The counter term of a given graph is a Taylor expansion up to the divergence of the graph. This is the overall divergence of the graph at a minimal energy given with the momentum equal to the mass, for instance, of a certain whole term, which is called the prepared amplitude of the graph. And this prepared amplitude of the graph is computed with a recursive formula. First, we start with the usual amplitude, Feynman amplitude of the graph, and then we add some terms in which, in the big graph containing all the subdivergences, we extracted graph by graph all the subdivergences. We compute separately the counter term of the subdivergence and the amplitude of the remaining part of the graph, and we put all together with this recursive formula. So it's a huge formula. So if the graph is small, like the two examples, of course, it's just a few steps, we are done. But if the graph has many subdivergences, then this formula really becomes huge. Okay, so here is the Hopf algebra of Connes-Kreimer, which is a mirror of this formula. So as an algebra, we take the free commutative algebra generated by Feynman graphs, which are one particle irreducible and divergent. I forgot here to say divergent one particle graphs. So like these ones, for instance, these two and others. The coproduct takes a graph and splits it into two parts. And so I forgot to say what is the recursive way to compute the amplitude, the renormalized amplitude for the graph, but it's written here. It's almost the same as the previous one. So you can see that there is an exact relationship between BPHZ formula and the expression of the coproduct and the antipode in this Hopf algebra. So as you see, the BPHZ formula is just the computation of the coproduct for the amplitude. Well, so starting from the coproduct, we apply the amplitude on the leftmost graphs, the counterterm map on the rightmost graph, and we put all together. So it is a convolution of this coproduct. In few words, BPHZ formula is just the convolution of two maps, the amplitude and the counter term, starting from this Connes-Kreimer coproduct on Feynman graphs. And exactly in the same way, you can see that there is a relationship between the counter term of each graph and the formal expression of the antipode. What is missing here is the Taylor expansion, which is an extra operator beside the usual convolution product. Okay, here is an example of a coproduct in this Hopf algebra. You take a big graph, and so all this formula here amounts to extract one by one the subloops, the subdivergent graphs. So for instance, in this graph here, one can take the whole graph and then extracting nothing, and we have a primitive element. Or we can extract just one loop, and we have two different loops that we can extract separately. So we have two terms, which are of the form one extracted loop and the remaining graph. Or we can extract both loops at the same time. And then we have a polynomial, a square of a loop on the right-hand side, and just the root, the remaining root of the graph on the other side. Or the other way, the final thing that you can do is you extract the whole of the graph as a divergent graph. And what remains is the free propagator, which is assimilated to the unit in this algebra. Okay, so to summarize this page, the amplitudes, the Feynman amplitudes are algebra maps from the Connes-Kreimer Hopf algebra to the algebra which contains the value of Feynman graphs. there is no more any coupling constant in here, but the Planck constant remain in the coefficients of the coefficients of the series. So in the amplitude of the graph, we still have the Planck constant, but in a finite number. So it's just polynomials in the Planck constant. They are not divergent series, asymptotic series in the powers of the Planck constant. And the counterterms, they are also algebra maps from the same Hopf algebra to the scalar algebra, but which must be seen inside this algebra, because then we have to put the parameter, the regularization parameter back to its original value. Okay, so why do we use Hopf algebras?
Excuse me. Once again, what is the A epsilon of H1?
This A here is the algebra where we take the value of the free, starting from the free propagator, we have immediately an algebra given where the whole theory takes place. It's the algebra which contains the value of the propagators. So it's the algebra where we are going to compute this green, the coefficients of the green function. So the whole green function is a series.
Only of the propagator or all of all green functions?
All green functions, finally, because all the coefficients of the green functions are just combination of free propagators using Feynman rules. So they are multiplication of this. So if you take a Feynman rule on a, in order to compute an amplitude for a graph, you will have a product of the free propagators.
You have more arguments. Sorry? But you have more arguments if you have a green function with the k points green functions. You have more arguments. So it's the algebra of, I mean, the tensor algebra of all the possible functions of the momenta or of the coordinates.
No, as you see here, there are no momenta written anywhere. I do agree with you. What I'm doing here is not a bundled version of the whole theory. What is missing by now is really the taking into account the space-time points or the momenta. So building up this theory as a bundle theory on the momenta. I'm just talking about the ingredients at fixed momenta, external moments. So I fix the space-time points or the external momenta, and I look what happens inside, and I just analyze that. So momenta are fixed here. External momenta are fixed. I do not care about the dependence of this series from the external momenta. I'm just talking the nature of one of such objects at given momenta, external momenta.
But okay. Then the algebra reduces to numbers. I don't understand.
No, not really, not necessary. It reduces to numbers for scalar theory, but for quantum electrodynamics, we have, I mean, that's why I wrote down here this free propagator for quantum electrodynamics, is to show you that there is a Dirac matrix here.
Okay.
This Dirac matrix tells you that the free propagator for fermions is a matrix.
Okay.
It is not scalar. Of course, the Lagrangian is scalar, because the Lagrangian, here is it. Okay. You are going to have a combination of all the ingredients, which are matrices, which are going to be multiplied in such a way that at the end you have a scalar element. Okay. And you need anti-fermions in order to make it scalar, the Lagrangian. Okay?
Yeah, it's clear at this point. Thank you. I just would like to recall you that you have more or less 15 minutes to go. So it's getting short of time.
Yeah, I go further. Okay, so what I wanted to point out that having a Hopf algebra to work with means linearizing a group, and this is an issue for many algorithms. Okay, so now let's go to group side. So proalgebraic groups are just inductive, projective limits of algebraic groups, and algebraic groups are very well known. They are the most of matrix groups are algebraic. Here is a list of algebraic groups that everybody knows. So algebraic groups are those groups who are practically given by their coordinate ring, which is a Hopf algebra. So the coordinate ring is just the usual polynomial ring of just Cartesian coordinates, as we are used from high school computations. And if we compute the coordinate ring for a group, then we have an extra operation, which is the coproduct, which is dual to the group law of the algebraic variety. Okay, I hope everybody is acquainted with algebraic groups in this audience. If you have questions, please do ask. So I give a formal definition. An algebraic group is a representable functor from commutative and associative algebras over a given ground field K to the category of groups. So it's a functor in the sense for any given algebra A, you have a group associated. Example, SL2. So you take 2 by 2 matrices with coefficients in the real numbers. Well, you have a certain equation which is given by the fact that the determinant of matrices must be equal to 1 in order to have SL2 matrices. But you can change the coefficients of the matrix and consider SL2 over the complex numbers or SL2 over any commutative algebra A. So the algebraic group is SL2, and it is a functor. And here, when we specify that it has coefficients in R, we are exactly dealing with the specific group associated to a given algebra A, which in this case is A equals R, the real numbers, okay? But the group law does not depend on the choice of the algebra A. It is just a group law which is given by the functor in a functorial way, okay? So this is an algebraic group. And so formally, such a functor, a representable functor, gives rise to groups if and only if the representable object here, H, this algebra, commutative algebra, which is here, which represents the functor in Yoneda terms. So this representable algebra object here, H, is a Hopf algebra. Does everybody know what a Hopf algebra is? It is an algebra, so with a multiplication and the unit plus the coproduct, co-unit and antipode, satisfying suitable operation, okay? So in fact, everybody knows this Hopf algebra because it is just the dual Hopf algebra of the enveloping algebra of the Lie algebra of the group. So it's the same. It's just the dual Hopf algebra. It contains exactly the same informations. Okay, it's just a different point of view on algebraic groups. Okay, so the duality goes like this. Algebraic groups are finitely generated commutative Hopf algebras. So they are exactly the same. So they can be identified in the following sense. Starting from a group, one defines H to be the coordinate ring of the group with scalar coefficients, so G of K, of the functor applied to the algebra K. It can also be seen as the set of regular functions on the group G with values in A, but then the functions need to have values in A and not in K. So they are not scalar functions, they are functions with value in A. And then it's the same, exactly the same ring. And then this H becomes a Hopf algebra with the coproduct, which is dual to the product law, the co-unit, which is dual to the unit in the group, and the antipode, which is dual to the inversion on the group. Okay, those who are working on quantum groups perfectly know all this stuff. On the other way around, starting with the commutative...
It's 10 minutes to the 1 hour talk.
Yes, thanks.
Just 10 minutes warning.
Yeah, thanks. On the other side, a commutative Hopf algebra H gives rise to the group by convolution. So we start with the Hopf algebra structure. We take the convolution of the coproduct, and we have a convolution product, which is the group law. Okay, and unit at inversion are given similarly. So a proalgebraic group is just the same thing, but the algebra H is not finitely generated. It is infinitely generated, so we have an infinite number of generators. And so, for instance, infinite matrices, upper triangular matrices, like this example here. So they are projective limits of algebraic groups, and the dual Hopf algebra is an inductive limit of a finitely generated Hopf algebra. Okay, so for quantum field theory, we have two groups which are important. The groups of invertible series. So they are formal series in the power of a parameter that I call lambda, like the coupling constant in physics, which start by 1. And the group law is the pointwise product of these two, as they were just the usual pointwise product of formal series. The Hopf algebra is well known. Okay, so it's called the Hopf algebra of symmetric functions in combinatorics. And then we have a second group, which is interesting, which is the diffeomorphisms group, which are formal series, but now I put a scaled relationship between the powers of the coupling constant of the parameter lambda and the coefficient. So these formal series are composed with the substitution law. I take the whole series and I put it at the place of the variable lambda in the next series. Okay, so this group is also pro-algebraic, and it is represented by the Faà di Bruno Hopf algebra, which is the following formula, which is just a formula which is the coproduct is linear on one side and polynomial in the generators on the other side. The coproduct here is given by the very well-known Lagrangian inversion formula. Okay, then formally we have a Connes-Kreimer Hopf algebra generated by one particularly reducible divergent graphs for a given theory, and then we can define the group, the dual group, which is called the group of formal diffeomorphisms by Connes-Kreimer. So this group is formally a set of formal series in a formal parameter lambda, in such a way that we can separate each the coefficient of each graph. So they are formal series spanned by Feynman graphs. In order to really distinguish the coefficients of different graphs, we need to put a label for the graphs. And this label, following what happens with formal diffeomorphisms, I've put it in the powers of the symbol lambda. So we have here a symbol lambda to the power a graph, which is really symbolic. In this sense, these series are not real. They cannot be computed. The elements here cannot be evaluated on a value, on a specific value of lambda, not even in an asymptotic way. No way, because lambda to the power a Feynman graph does not exist. Okay. Okay. So the real to the virtual relationship is exactly the relationship between the Faà di Bruno and the Connes-Kreimer Hopf algebra, and therefore the projection from these diffeomorphisms to the formal diffeomorphisms. So the relationship is just that you send each Feynman graph to the number of its vertices or its loop number, whatever. Okay, so I think I will skip these integral BPHZ formulas. So this is the topic in which we can improve the BPHZ formula on an integral version of the formula. So this is the formula. I tell you that BPHZ on graph is the computation of each counterterm, and what I'm saying is that one can sum up all the Feynman graphs to a given number of vertices, define these new generators, which are now integral generators. And what I pretend is that this BPHZ formula can be defined directly on the sum of these Feynman graphs. And so it gives an integral BPHZ formula. It's not the main topic of my talk, so I'll go on because I have 1 minute to finish. Sorry, so I want to extend all these to non-commutative coefficients. And so the point is that I would like to keep care of this functorial procedure in order to renormalize all theories independently of the algebra A. So for this, I need a functorial definition of my renormalization formulas. So something which is compatible with this duality between Hopf algebras and groups. Okay, so for fermions and gauge theories, this is not possible because the functors in algebraic geometry only apply to commutative algebras and not to non-commutative algebras. So there exist commutative Hopf algebras of renormalization, which were introduced mainly by Walter van Soeslekom, but they are not functorial in the sense that each theory requires its a specific Hopf algebra and not just one Hopf algebra, therefore only one formal group for all the theories. So what I'm looking for is a functorial theory. So this functorial theory, there were hints that it could exist because there was a non-commutative Hopf algebra already defined for quantum electrodynamics. And so there is a way to extend these formulas to a non-commutative context, even if formally in mathematics one cannot define a functor for the diffeomorphism group to associative algebra, because the composition of series is not associative when the series have non-commutative coefficients. So there is a problem, a clear problem in the composition of formal series for series with non-commutative coefficients. So how could we define such a functor for the diffeomorphism group? So the trick is the following one. We replace the tensor product of two algebras together with its tensor product algebra structure, which is this law here. It's component by component product. We replace this tensor product by the so-called free product algebra. This free product is in reality a coproduct in the categorical term. So the free product of algebra is just the concatenation of all terms. So we have two algebras, A and B. I take pairs of elements in A and in B, and I want to multiply them. Instead of multiplying term by term inside A and inside B, I just concatenate them. What I get, of course, are longer terms in the power. So I have length. I have terms of any length in alternative sequences of elements of A and B. Okay, so this is called the free product algebra, and it allows to define a folding map for any multiplication in an algebra A, which is an algebra map and solves entirely the problem. So this procedure has been already settled by Daniel Kahn in the 50s. He invented the so-called co-groups in a given category. So co-groups in a given category are exactly they are the replacement of Hopf algebras, but in different categories than commutative algebras. So Hopf algebras are co-groups in commutative algebras. The analog in other categories are called co-groups in the given category. So co-groups in associative algebras exist. And so one can formally do algebraic geometry in terms of these co-groups. And so this is what we can do for invertible series, that is renormalization factors. We can completely deal all renormalization factors in this sense for quantum electrodynamics. It fully makes sense. So it gives rise to a cogroup in associative algebra. Okay, so this gives a good algorithm for modeling renormalization factors in quantum field theory in the case of fermions and gauge bosons. The problem with diffeomorphisms, so the coupling constant, is that the diffeomorphisms still do not make a group. They really do not make a group. It's not a matter of functorial, yes or no. It's just that formal diffeomorphism of series with non-commutative coefficients, they just do not form a group because the composition is not associative. And so if we compute the associator of three series with respect to the composition, we see that at the first non-trivial order, already we have something which doesn't work if the coefficients do not commute each other. So here we have the first term where B, the terms for B and C series here are inverted. So it is not a group. 1 minute to finish. The solution is to relax groups into non-associative groups, which are called loops by Ruth Mufang in 35. So loops are those sets with a multiplication, a unit, a left and a right division. So we can define on the left, define on the right. There is, therefore, since there is a unit, one can define the inverse of any element from the left and from the right. They do not necessarily coincide, okay? And all the properties here that one has to require are made in such a way that formally these two equations here have unique solutions in loops. The two equations are the following: A times X equals B should have a unique solution X, which is given in terms of the division. It's B divided by A from the left. And the equation Y times A equals B has a unique solution, which is it's B divided by A on the right. Okay, so given these loops, of course, groups are just a particular case of loops. They are associative ones. And in groups, the inverse is unique, and the division is just the multiplication by the inverse. Okay, the smallest smooth loop, which is not a group, is very well known. It's the sphere of dimension 7, the unit octonions, and it is used together with a Hopf vibration to describe the quantum bits in for two states, correlated states in quantum bits. So I go further, the geometrical terms. My last result is the construction of explicit codivision and antipode for the coloops in associative algebras. So finally, I've computed them. The theorem is that there exists a coloop for formal diffeomorphisms with an explicit formula for the divisions. One of the two is the usual Lagrange inversion formula in a non-commutative context. The other one is a completely new formula, very complicated. And what happens is that in the loop of formal diffeomorphisms, a miracle happens. The inverse is unique, and the division on the right is the composition by the inverse. And because of these two properties, the renormalization formulas of Dyson can be applied to loops instead of groups. So the conclusion is that one can think about renormalization in terms of these non-associative groups with a specific property that the inverse is unique, which is a diffeomorphism group, which is exactly diffeomorphism loop, which is exactly the loop. Diffeomorphism loop is the one which renormalizes the coupling constant. And so the conclusion is okay. Said my plan worked. What I announced, I was able to construct it. The perspective, I'm not just repeating what I just said. The perspective, what I'm interested into is to tell you that, in fact, if so, we could settle a real functorial renormalization theory in quantum field theory, which would be just one procedure for all theories if we renounce to associativity in the renormalization group. But this associativity of the renormalization group, so if we talk about the renormalization group flow in the for the running parameter, this associativity is related to the fact that we find the solutions as a solution of flow equations. But these flow equations could be settled in the realm of loops, smooth loops, instead of groups. And then eventually think of having non-associative solutions. So this is possible because the mathematical setup has been fixed by Lev Sabining in a book, in a huge book on smooth loops. And so what I want to point out is that the next step would be to compare with the experiments. Can one really prove that the renormalization procedure must be associative? In fact, we all know that renormalization cannot, since it deals with a quantum theory, cannot be really reproduced. So it's an assumption that it is an associative procedure. I don't think we can really prove it. In any way, it's an open question. Could we think of a renormalization procedure which is non-associative? Mathematics tells you yes, one can do it. Okay, thank you very much for your attention.
Thank you. Thank you, Alessandra. And there was some question during the talk. Are there further questions or comments?
One question. At some point you.
Can you speak louder, please?
Can you understand? Do you hear me?
I can hear you. Yes.
Yes. Okay. At some point, when when you were writing the renormalization group equation, you wrote lambda 1 of lambda 0 of lambda, something like that. What was this lambda 1? This function, yes. Lambda 1 of its argument, I couldn't understand.
Yes, it's here. Precisely. So lambda is a physical parameter. So for instance, the electric charge. Okay.
Yeah, I know lambda 1. What is the function lambda 1 of its argument?
Lambda 1 is a second renormalization. So we start, suppose that we want to compute lambda at a certain scale, and we start with the scale in which the energy is 0, so there is no coupling, okay? So, but we want to compute it at the real scale here. So we have to go from, so we have to produce lambda at our scale, starting from a bare value, which is the lambda 0, that we need to, it's a fiction, of course, but it's what we formally have to introduce in order to take into account our formulas, which go from a bare situation of energy 0, it's the perturbative situation, to our scale. Then suppose that instead of doing a direct step from energy 0 to our, or energy infinity, I don't know how you want to say it, we make it in 2 steps instead of just one. We do it in 2 steps. This is the associativity of the group, yes. Of renormalization. Okay, we apply 2 renormalizations, and we have a final one. Okay, so what is the renormalization group law here? Well, if you go from one scale to another one, so you need to recover lambda from lambda 0. And and then we apply to another change of scale. So we want to recover lambda 0 from a lambda 1 scale. And then finally, we want to understand how to recover lambda from lambda 1.
Excuse me, lambda 1 there is not an argument. It's a new function. You are introducing a new function.
Yes.
So how is it defined?
Lambda 1 is just...
It should be the same function, no? As far as I understand.
It is formally the same function as lambda 0.
Okay.
You want to understand why is it a different name as a function?
Yes,
because,
yes.
Yeah, because as a function of lambda, it contains, it is a formal series which contains coefficients which are computed here, which are computed using, sorry, where did I, well, in fact, I didn't write it down. It was just, but it contains the counterterms. I didn't, well, it's here. You can see it here. It contains the zi's contains counterterms for the graph at a certain energy.
Yes.
Okay, so then I change the scale, and then I have a different function because it depends on the z's.
Yeah, but I don't understand. I mean, it should be, if it's associative, the rule is the same. You just apply it twice. So the function should be the same.
So what you mean is that this, as a formal function of its parameter, should be lambda 0.
Yes.
Okay, well, even if you require this.
Momento. Yes, sorry.
Yes, even if you require formally lambda 1 to be the same function of its variable, so to be, in fact, lambda 0 of lambda applied again.
Yes.
Even if you require this in loops, usually lambda square. I mean, there is no need to have a power associative group at the end. So a group which is non-associative doesn't necessarily satisfy the power associativity relationship. What I mean is that in a loop, if you have a formal series A and you take the power a squared, a to the power 3, a to the power 4, you formally don't have a squared times a squared equals a to the 4th. This is an extra property, which is called power associativity.
Yes.
Okay, so so even if the series is the same, it doesn't necessarily require, it doesn't necessarily imply associativity.
Yes.
Okay, so I would like to suggest to postpone the further discussion of this point to later, because it's getting late, and I would like first to know whether there are some other urgent questions for Alessandra Frabetti. If this is not the case, I would like to thank again Alessandra. We formally close the seminar here. I can stop the recording, but everybody is welcome to continue the discussion with Alessandra and with more specific questions. Let me just recall that our seminars on non-commutative geometry and physics will start again later after the summertime. Thank you.